Everything is okay? Yeah. Okay, so hi everyone, thanks for coming. This is the diffusion and generation session. The first paper is CLR wire towards continuous latent representations for 3D curve wireframe generation. The speaker is Hui Huang.
Okay, thanks for the introduction. So this work is about clear wire towards the continuous latent representations for 3D curve wireframe generation. So 3D curve wireframes, also known as curve networks, are compact yet expressive geometric representation that captures the structural features of the object surfaces. So they are widely used in 3D modeling and design. Over the years, various works have explored their potential So early in 2015, Intel proposed a reconstruction method that generates detailed surfaces from the sparse curve networks, showing how wireframes can guide the full 3D surface creation. So more recently, Li et al. Introduced an interactive system for the curve network modeling in VR, so allowing designers to build and refine 3D forms directly in the virtual space. So recent work also focused on the directly generating 3D wireframes, such as BBREP-Gen, a multi-stage diffusion-based framework. It first generates the face patches, then progressively refines edge and vertex structures conditioned on those faces. We introduced the 3D wire in ECCV last year, an autoregressive model that contrasts wireframes by generating the line segments one by one. However, a key limitation is their lack of the explicit topological modeling. They don't clearly capture how geometric elements collect and related to one another. So instead of the direct generation, Xu et al. Proposed a technique that combines geometric priors with optimum transport to recover sharp edges from noisy point data. Zhu et al. Developed LRVE, which predicts the voxel-level collectivity to extract the line segments and reconstruct sharp structures edges. So while effective, so their approaches often fall short when it comes to extracting more semantically meaningful or descriptive curves. So to representing an object structure more effectively, we propose ClearWire, so a method that's jointly modeling geometry and topology in a continuous latent space. So this unified representation not only preserves structural relationships, but also supports a range of the downstream tasks such as interpolation, generation, reconstruction, and editing. So before diving into the method, let's first look at how we represent 3D wireframes, which can be broken down into the individual curve segments. We start by normalizing each curve to remove spatial redundancy like position and scale. This helps us to represent curves in a consistent form, regardless of where they appear or how large they are. It also makes training easier, actually, allowing the model to focus on the intrinsic shapes of the curves rather than being distracted by the external variations. So we'll further construct an explicit representation for the entire 3D wireframe. Each curve is described by its normalized shape and the coordinates of its two endpoints. This captures its geometry. We model the collectivity between the curves using an adjacent list based on shared endpoints, and we design a validity flag to each curve, which allows us to handle wireframes with different number of curves. So this representation forms the foundation of our learning framework. So now let's work through our method, which consists of an encoder and a decoder. So in the encoder stage, we starting by encoding each of the normalized curve to get its latent, curve latent. At the same time, we encode the coordinates of the curve's endpoints along with their topological collection. So these two embeddings are fused into a structure-aware representation. Then we apply a cross attention where learnable queries attend to those fused features and we extract a fixed length global latent for the entire wireframe. So in the decoder stage, our goal is to reconstruct the complete 3D wireframe from their global latent. We decode it into the 3 components: the geometry of each curve and the coordinates of their endpoints, the topological collection between curves, and a validated flag for each curve. So in this way, we decode a complete 3D wireframe from a compact continuous representation. So after obtaining the wireframe's latent, we further introduce the latent flow matching to model the mapping between the latent space and a Gaussian distribution. Once training is complete, we can sample a Gaussian noise and use the transformer to map it into a wireframe latent. Finally, this latent is decoded into a full 3D wireframe, capturing both geometry and topology. So based on this unified and continuous latent space, we can smoothly interpolate not only the geometry but also the topology between the 2 wireframes, so enabling seamless transition across structurally different shapes. Moreover, our interpolation naturally extends to the multiple wireframes, enabling smooth transition across a series of shapes with varying geometry and topology. And importantly, the interpolation path remains smooth even when hooping back to the original shape, demonstrating the consistency of our latent space. Here we show more interpolation results. Our method is able to generate a smooth and coherent transition between different samples, both in terms of the geometry and the topological structure. This further demonstrates the consistency and the expressiveness of the learned latent space. Based on the smooth latent space, our method can progressively generate diverse 3D curve wireframes from the Gaussian noise, capturing both geometry and topology in a coherent structure. So we also compare with the existing methods such as BRAPGen, DeepCAD, and 3DWire. So our approach is capable of generating more flexible wireframe structure with diverse curve shapes. Here we show a comparison of the wireframe generation condition on the point clouds. So as illustrated, existing method can only recover the sharp edges of the shape, whereas our method generates a complete, clean, and semantically descriptive curve structures. We also evaluate our model on the partial point cloud inputs. Even with the incomplete observations, our method is still able to generate complete and coherent wireframe structures. In addition, we conditioned our generation on the input images. So as showing, our method can generate structurally complete 3D wireframes guided by the visual information contained in the image. We also explore the ability of our model to generate 3D wireframes from sketches. The results show that our method can interpret both the geometric and structural cues from sketches and further generate complete and even novel wireframe structures. So we conduct the quantitative evaluation under 2 settings, unconditional generation and point cloud conditional generation. So in both settings, our method achieves a better performance. So here we represent more results from the unconditional generation setting, as showing our method is capable of generating 3D wireframe with diverse shapes and complex structural pattern. So here's more. Okay, well, still there are some failing cases, such as self-intersections, component misalignment, topological error, and redundant curves. So we may consider introduce regularization or spatial consistency constraints and or topology graph constraints to further improve the integrity and editable of the generated wireframes. So to wrap up, so we propose a method that unifies both geometry and topology into a single continuous latent space. This joint modeling allows the network to understand not only what the shape is, but also how it is collected structurally. Since we built a continuous latent space, our model enables smooth interpolation across different shapes. It moves us actually one step closer to the editable and interactive 3D shape generation. We believe this can open up a new possibility in CAD's design tools and generative modeling tasks. So thank you for listening. So more detail can be found from our project page, code and data available too. Thanks again.